for the excited states of conjugated bonds.
Thank you.
So the person who got given my key, could I have it back, please? Someone who was given a key? It was someone in my camp, one of our postdocs had. Thank you.
All right. Everybody can see the Hulk all right? Details fine? Yeah. All right. All right, so green energy. Right, so as we've heard, we all have a bit of a problem. It's not that Easter's coming early this year. It's that we're burning a lot of oil and coal, gas, changing the atmosphere. Nobody really knows what's going to happen, but it's likely to be bad because happy human life is a generally fragile thing. In order to avert the possibility of something really bad happening, we need new energy sources. And on this front, actually, there's a lot of thought that what one wants to do is use the energy of the sun because it appears to be all over the place and the sun is not in danger of burning out anytime soon. There's plenty of energy to power things if we can only harness it, as nature does all the time with a complicated array of molecular machinery. And without a lot of very toxic waste. Now along these lines, one avenue of inquiry is the dye-sensitized solar cell, which is not quite like many of the solar cells that have been discussed at this meeting, many of which have been bulk heterojunction solar cells. The basic idea behind a dye-sensitized solar cell is that you have an electrode, transparent electrode, a glass plate, and some semiconductor, usually titanium oxide. And there's a bunch of dye on the semiconductor, and what happens is that the dye intercepts the light, the dye gets excited. Over here, the energy levels, it's easier to explain. Dye gets excited, the dye is more easily ionized in its excited state. So it passes an electron to the semiconductor, and the electron goes off, makes a current. Meanwhile, there's a redox couple here in a solution or somewhere near the dye that gradually fills in the charge that was depleted in the dye, and then the dye is returned to its ground state, once again whole. Now in order to make these things, you need dyes, obviously. There are basically two broad classes of dye. One of these is organometallics, and Ben Powell talked a lot about these. Another are the metal-free dyes. The metal-free dyes tend to have certain things in common. They all have a structure that's broadly like this, or like this in a little bit more of a schematic view. They're all conjugated organic systems, and what this basically means is that you can usually draw two Lewis structures that are low-lying. One where charge is on one end under the molecule, one where it is on the, or, sorry, this molecule is neutral. Okay. One Lewis structure where the molecule is neutral, as you might expect, and just drawing it, connecting the bonds as you might. Another word is a Zwitter ion, where you basically push the charge to one side. So actually, there is a charge that's moving backwards and forwards here. It's just that you don't, here basically, you don't see it. Here you create a dipole because you have nuclei over here that are creating compensating charge. All right, so the basic story is that over on one end, you've got some fragment. The fragment has a box. The fragment likes to have two electrons in the box. It makes it happy. On the other end, you've got another fragment. There's another box. This fragment likes also to have two electrons in its box. Maybe not so happy, not so keen. In the middle, you have something that's usually called a pi bridge or a spacer, and this generally consists of things that don't like to have two electrons in the box at all. right? So this charge movement actually is through virtual states, where you move the charge from one end of the molecule to the other. You never actually observe it on any of the intervening sites. Okay, so the molecule gets excited. If these two ends were symmetrical, if both of the boxes were perfectly happy, then the ground state would be an even combination of this, and the excited state would be odd. As you detune this resonance, one of these comes to dominate the ground state, and the other comes to dominate the excited state. So if this dominates in the ground state, then you excite this thing, the charge moves over here, this electron moves over here where it's close to the semiconductor, and it can hop off and do some work for us. Everybody's happy. Except maybe the dye loses an electron. Now, in order to understand how we might make these things better, we basically want to understand how we can put together fragments, and notice that these are all basically a little bit like Legos. You tend to see motifs again and again. How can we put these motifs together to get something that does what we want, in a general sense? The modular character suggests that maybe this can be simplified. We may be able to create a simple model that will guide us in how to assemble these things and make better dyes, which is a lot like what Johannes was talking about earlier today. Now, this talk is going to be about computation, but really my goal is not to show you a bunch of numbers. My goal here is basically to show you how you can use models to understand what's going on in molecules. Right, I want to communicate a heuristic strategy, and like Ben Powell pointed out earlier, and Michael Berry before him, and apparently someone before Michael Berry, it's good to do things with examples. So I'm going to do this with an example, basically. It's, there'll also be a little bit of plugging of recent publications, but I'm hoping to keep this a little bit subtle. The print will always be small on the bottom of the slide. So first, if I want to understand what a structure-property relationship is, or how I can describe them, I'd better understand what it is. And structure-property relationships are basically just chemical speak for knowing what's going on, or more generally, a sort of loose generalization of the ideas of topology and distance to a chemical space, where you have basically the set, I guess it's not a space, you can't add them together, but a set of all sorts of different molecules where you've made some change. Right? And what we want to, the concept one wants to apply that is somewhat like distance is the idea that if I make a small change to a molecule, the effect should also be small. And I would like it if I could actually order the substituents, these little guys I'm attaching, and the effects that they bring to the molecular properties. A good example of this, which is well known to some extent, I don't think I knew about this until after I was out of graduate school. But then my education took a somewhat windy course. But a good example, the most well-known, probably is the Hammett equation. There are actually three Hammett equations. It's often called a free energy relationship because you can write it like this, and what this says is that the free energy, basically, between a product and a reactant goes as the free energy of the reaction, some reference reaction, plus something that is a product of two numbers. One of these numbers is called a structure constant. It is supposed to depend not on the substituent. This other number, sigma, is something called a substituent constant, and it does depend on the substituent. So you can think of sigma as a property of the substituent, or at least you're supposed to, and rho basically includes everything else. It might include the solvent. It definitely includes the reaction that is taking place. Different reactions, if you go and look up in a table, different reactions will have different structure constants. You're supposed to plug in a sigma, you get a free energy. Because there is a relationship between the equilibrium constant and the free energy change, which we are all taught in first year, or you take first year, you're taught it in first year, take my first year, I taught it first year, taught it to you. Such that the equilibrium constant is the log, or the log of the equilibrium constant is the free energy change. So you can also write this as log K naught plus rho sigma. If detailed balance holds, you can do this yet again. And you can come up with an expression for the rate. So you have a rate of transfer over this barrier, and this is equal to the rate of the transfer for some reference reaction, again, plus rho sigma, same rho sigma. So, Lewis Hammett actually discovered, or he tabulated these sigma constants for a particular reaction, and that was the dissociation of benzoic acid and water. He did this a while ago. But it was quickly discovered, partly by him and then subsequently by a whole lot of other people, that if you take these constants, you can actually apply them to all sorts of different reactions. And they correlate, they make lines. The way you play the game is that you have something that you're interested in, you plot this on the y-axis, you plot Hammett constants. On the x-axis, you fit a line to it, boom, you're in business. Maybe you publish a paper, you have a nice figure, anyway. What you see here, well, I mean, the fact that you can do this implies something powerful, because if the electrons in the molecule are quantum mechanical, and if quantum mechanics tells us that the answer you get depends upon the question that you ask, what this is basically saying is that all these reactions are asking something very similar of the substituent. Right? And that this thing matters, it might be general. What is generally thought is that this is the question that's being asked. Alternatively, brother, could you spare an electron? Right? One electron. Now, if you know something about the Hammett equation, you might know that there are different sets of parameters, and these basically, I would sort of say that these represent a proliferation of contractual details in the lean of the electron, right? We mortgage some reactivity for an electron or vice versa. Okay, I'll take your electron, but I really insist that I'm going to take the electron density from number 2 in the ring. Something like this. But the point is that you can apply it in a lot of situations. And there is some basis for this in theory. In particular, it's been said that if you calculate molecular orbitals, we've all heard the terms HOMO and LUMO in this meeting, then you can rationalize Hammett's trends by saying that if you take some HOMO or a LUMO and then take the substituent orbital, bring them together, you perturb the HOMO or LUMO of the complex of the substituent and the substrate, you react this with something else, and then that reaction actually will go very often as a log of the gap between the HOMO and LUMO pairs on the reacting species. And so this rationalizes the Hammett correlations, but what I really want to point out is that the whole concept of a reaction series, which is inherent in the Hammett relation, the idea that you have a set of reactions that has some continuity, some ordering, where small changes in the substituent constant produce large changes in the rate, and you can connect these, is basically entirely determined, or very dependent on the fact that these orbitals are not changing very much. Right? So if when this little fluorine was tagged onto this ring, the orbital suddenly changed entirely, you wouldn't get a very nice relationship. You wouldn't get a line. So that really, if you want to understand structure-property relationships, you should be paying attention to the state. And this is important because there are many ways to come up with molecular orbitals. One is to just make them up, right? In fact, I mean, if you do something like Huckel theory, then this is a good guess for the orbitals. In fact, they're never really implicitly defined. We just define the Hamiltonian. But there are many other ways to make orbitals that are explicit. Usually these are self-consistent field techniques as a broad family. And frequently, as I was mentioning after Johannes' talk, when you have a self-consistent field, you have a nonlinear problem, and actually there are multiple solutions. So it's not the case that necessarily there's one HOMO and one LUMO, and that if you calculate something by a particular method, if you have a non-well-behaved system, you're always going to get the same pair. So you have to pay attention to the shape of the state. Now, it turns out actually that one of the reactions you can apply this thing to, or that it has been applied to, is an excited state reaction. And this is interesting to us if we want to actually understand the excited states of dyes. In this particular case, the Hammett relationship was applied through photoisomerization of this hemistylbene hemithioindigo species. It actually has good correlations. But what I would suggest to you is that maybe this is not as surprising as you might think. I don't know if you think it's surprising. Because really photoisomerization is a two-site problem. We know this because ethylene photoisomerizes, and ethylene only has 2 pi orbitals and 2 sites. If you have a definite bonding structure, one double bonding structure with single bond alternation that is definite, then in a way you can map this to ethylene. There's clearly one bond in this molecule that a cis-trans photoisomerization would occur by. It should be a two-site problem. So what happens with conjugated dyes? I told you at the beginning of the talk that actually there are multiple Lewis structures. Perhaps it is no longer a two-site problem. In fact, there is good reason to think this. I can show it to you here. So, for the example we just looked at, you light up the molecule twists, it twists along the double bond. In fact, that's exactly what this molecule does here. This is a very stable Lewis structure. If you were to separate charge here, you'd pay a big price. If you excite, you flip around one bond. You don't flip around the other bond. You deprotonate this molecule, you make an anion, suddenly you have a resonance. The two ends of the molecule are approximately equal in energy, and now you can go both ways. So there are 2 reaction pathways. This should not fit into a Hammett picture. Ultimately, I'm going to give the plot away, it's not a two-site problem. It turns out that you can understand this, though, in a way that's sort of like what I was saying about the Hammett relation. And to do this, basically, you start with a theory that goes back a little bit of a ways. It turns out that dyes like this were being studied a lot in Kodak labs around the middle of the last century, back when they made Kodachrome. And there were a lot of experiments done on dyes like this by a man named Leslie Brooker, and what he determined was an empirical rule that says, for the color of the dye, if you have a dye that is asymmetric, take this one here, and you take its symmetric parent dyes, then the wavelength of the asymmetric dye is no redder than the mean wavelength of the symmetric parents. And, he said, the deviation from this red limit should depend upon the basicity difference of the 2 rings. Now, this is the way he defined basicity. Sounds a little bit like the Hammett definition of the Hammett constant, in a way. But what Brooker did is he used his spectral data then to define chemical basicity scales for the rings in his dyes, and they agreed, more or less. Right? So again, if the answer you get depends upon the question you ask, maybe there is a question that's being asked that is common in general here. In fact, the connection with the Hammett idea goes a bit deeper. If you actually put a substituent with a Hammett constant on a ring in a dye like this, you find that the deviations in the spectrum are actually correlated with the Hammett constant. And if I told you that the Hammett constant can be expressed as a one-electron phenomenon, this is somewhat interesting because these Brooker basicities, the Brooker deviation, is the excitation of the whole dye. Right? It's not just one electron, and there are many electrons in the dye. But there's an indication that perhaps there is some signature of an effective orbital space that might correspond to this theory. Now, sometime after Brooker's experiments, J.R. Platt, who was also famous for naming the LA and LB states of benzene, came up with an empirical model to describe Brooker's results. And here's how he did it. It was a model Hamiltonian, entirely empirical. It's a 2x2 Hamiltonian. We define an iso-excitation energy to be the harmonic mean of the excitation energies of the parent dyes. Right? This is the energy corresponding to the mean wavelength of the symmetric parent dyes. We define a basicity difference to be everything else, essentially. Right? This is the formula for basicity difference. we can do this actually knowing that if we do this and then put BLR over 2 on the diagonal of this 2 by 2 matrix and diagonalize it, then we'll get the excitation energy of the dye. Pretty straightforward. So Platt formulated this empirical model. He took all of Brooker's data and he found something fairly interesting. He found that in fact what Brooker was saying made sense, and you could, within the limits of the experiments, write each Brooker basicity difference as a difference of Brooker basicities, where each basicity was a property of the ring and nothing else. It didn't depend upon whatever other rings that ring might be conjugated with in a given set. He basically did this by formulating consistency relationships like this, which say that if you've got some ring C on this side, then if you put in A and you put in B over here, that should actually be the same as if you have D and then A and B over here. And if you produce with a whole set of dyes, then you have a consistent set of basicities, where the basicities are independent properties of the dyes themselves. Now, I told you that if you pay attention to the state, there are actually solutions in quantum chemistry. There are problems in quantum chemistry with solutions that correspond to the Hammett equation. At the risk of setting up a straw man here, maybe we might wonder if there is a problem in quantum chemistry that would give us the resonance color theory as its solution over a set of dyes. The man is made of straw. There is such a solution. Without going into the technical details, I'll just say that the problem here is a state-averaged, complete active space, self-consistent field problem. It's a self-consistent field problem. It gives you orbitals. It gives you an orbital space, which I suggested we might find for this theory. And it gives you an orbital space with a particular structure, with one orbital on the bridge, one orbital on one ring, one orbital on the other ring. Right? Now, this looks a lot like the theory. In fact, I'm going to tell you that this self-consistent field is the resonance color theory. They're the same thing, like the chicken and the egg. Because here we've got one electron state per ring. It's very easy to find basicity differences. And you can switch the rings in and out if you want. And you can find this. Here's the most important thing to say. I should have made a slide for this just to remind me. You can do this with a whole lot of dyes. I'm only showing you one here. This is the dye that I happen to like. It happens to be useful for a lot of reasons I'll say momentarily. But you can do this with basically any monomethine dye that I've tried. So anything that's ring, bridge, ring. And I don't know, I've calculated this solution for a whole slew of these things now. You can always find it. They all have the same structure. These dyes are all dyes for which the resonance theory should hold. You can always find the same self-consistent field solution. If you go and you calculate the excitation energies with this onsite, or with this state, and for this technically multi-state, multi-reference, second-order perturbation theory, correlation consistent, double zeta basis MP2, again, double zeta correlation consistent basis geometry optimizations. You don't really need to know all that. It's just not, it's not Mickey Mouse, is what I'm saying. So if you go and you calculate all of these excitations, you find that in fact the Brooker deviation rule is obeyed. None of the asymmetric dyes are ever any redder than the symmetric parents from which they come. And here's what's really nice about this molecule. I've got an unhealthy love affair with this molecule. In fact, I think the last conversation I had with Chris Bardeen 8 years ago, we were walking down Goodwin Avenue talking about this same silly molecule. But look, here's the deal. Obviously the molecule is asymmetric, but it is electronically symmetric. If you pop a proton off and you get an anion, the Brooker deviation is almost zero. Put a proton on one end, what happens? Well, it shoots up. Boom. All the way out here now. In fact, all of these singly protonated states are all the way out here. Put another proton on the other end, so you've got a double protonated species, boom, you're back at resonance. Again, Brooker deviation is 0. This is actually a very nice dye for exploring the physics of conjugated systems, because you can move it very far to the poly limit, move it right back to the methine limit, just with protons. If you want something in between, there's actually another site here on this nitrogen. You can protonate it and get something intermediate. So with this one molecule, I can basically cover everything from a methane to a polyene in either direction. It's quite useful. But it does obey the rule that was stipulated in the theory. Furthermore, if you go and you do this, calculate the state for all the dyes in the set, there are about 29 independent dye structures here, find the state average CAS-SCF solutions, look at the localized orbital basis, they don't change much across each row. And this is exactly the pattern of transferability that you would expect from a theory that postulates basicities that depend upon one ring and not whatever ring it's conjugated with. Again, it's the structure of the relationship and the structure of the state. It's all in actually looking at the solution you get. We have the excitation energies. We have some inkling that there should be context-independent basicities. We can try and extract them. If we go back and use some of Platt's consistency conditions, we plot for different choices of B here, the difference between B and A over all C's. Did I get that right? Each A, I think, is a different line, and there was one B for all lines, and then the C's are all the little dots. The point is actually that all of these lines are really parallel. This means that you can move all of these affine scales onto a single scale with a single origin, and then you'll have a single scale for the basicity. I've done that, and then here are the results of that. What I want you to notice about this plot is that each of these, I mean, they're all sort of, I need a new graphing program, I guess. They're all sort of piled on top of one another. But really, if you just look at a particular color, they're all pretty strongly peaked. The possible exception of this guy in the middle. But even this isn't so bad. So using this, you can extract these BLR parameters that Platt was extracting from experiment when he did his work. And then if you go and you recalculate the excitation energies using the parameters in Platt's model, and you compare them with the multi-state, multi-reference state average CAS-SCF 4.3 correlation consistent PVDZ basis calculations, which I couldn't do with a pencil. I did them on the national facility. Then you get this line. Right, now the thing to notice about this line is that it's a line, right? Pretty straightforward. It's not a bad line. But the determination coefficient is pretty close to 1. And the residual for any of these calculations is less than 1,000 wave numbers, which is about 0.13 eV, which is well within the a priori expected accuracy of the calculations themselves. Right? So what this is saying is that basically, as far as that accuracy is concerned, this line is perfect. And what this says is that because I was looking at the state, I basically found that all these calculations, each of which take, not a huge amount of computer time, but again, you can't do it with a pencil. This entire set of dyes within Platt's model is parameterized by 14 numbers for 29 dyes. So you can spend a lot of time on computers, and in the end you get something that basically tells you that you have 14 numbers worth of information. But this justifies, this justifies the resonance color theory in a way. Everything that I've been saying justifies the theory, which was empirical. In a way, maybe it still is, I don't know. I haven't derived it from first principles yet. What is also really nice, I said some things earlier about the Hammett coefficient and one-electron effects. and the fact that the Brooker Basicity, although it was being measured by calculating the excitation energies of whole dyes, had some of the signatures of being a one-electron energy, an energy on a one-electron Hilbert space. I can actually show it to you now, because in this localized orbital basis, there's a very clear definition of what a one-electron energy is. It's the energy of an orbital, right? So if I want to go and I can use the same procedure to calculate one-electron basicities that I did to calculate many electron basicities from the excitation energies. And I plot them one against the other, and again, this line isn't bad. Again, this is r squared, by the way, it's not just r. Pretty close to 1. And what this basically tells you is that, in fact, the Brooker basicity is a one-electron property, which is nice. One-electron properties are simple. We like them. It also tells you some other interesting things, by the way. I suppose it tells you that really, if you look at what the base energy scale on this problem is, it's this proton. Both of these protonated rings down here, compared to both of these deprotonated rings up here. This energy difference is about as much energy as there is involved in the resonance itself, which is actually, maybe that's not surprising because I told you that when you protonate only one side, you basically have a polyene anyway. This relates somewhat to what Ross was saying earlier, actually, about the environment of dyes. Because if this thing is in a protic environment, you anticipate that there'll be fluctuations in the proton chemical potential around the sites. You can do a lot of damage. More than very deep electronic effects would anyway. Okay, so how much time do I have? Oh, okay, pretty close. All right, so basically that was, again, very subtly plugging a recent paper. So I've basically shown you that there's a simple theory that's justified. You get it back if you do expensive calculations. What else can you get out of it? Well, yeah, we have actually managed to get some new stuff out of it. I think it's new. I don't know. It's so easy. It might be old, but I haven't been able to find it. So Platt wrote down this Hamiltonian, right? Now, if you have a 2x2 Hamiltonian, you can diagonalize that. Even I can diagonalize a 2x2 matrix. It takes me a few minutes and a lot of erasers, but I can do it. You get the ground state. You find that, in fact, you get one of these basis states times the cosine of an angle, and the other basis state times the sine of an angle. The angle here is defined by a ratio between the diagonal and off-diagonal elements of the matrix, as so. Now, we generally have a feeling that when a dye is off resonance, the bond alternation changes. In fact, there's been a lot of hash made about this by people like Seth Martyr and Jean-Luc Verdot. And if we want to actually write or propose a bond alternation parameter, this is a natural choice, right? Each of this cosine squared and the sine squared are really just the populations of these two basis states. Each of these basis states is like this guy and this guy, so they each only have a double bond on one bond. It's a natural choice for a bond alternation coordinate. This, of course, high school trigonometry tells you that this is this, and then if you plug this into there, you get this. This function looks like this. And if you then go and compare this against the geometries that were used to calculate the excitation energies, you find it's not so bad. There's some phase ambiguity about the basicity here, so this is the absolute value on both axes. But again, now this isn't a line, but it is a one-parameter fit with the determination coefficient of about 0.9. And the highest residual, I guess, would be this guy here, and that's about 4 thousandths of an angstrom, which is not that bad. So in fact, once you've established this, you can go and you can do other things with it. Another thing that I'm not going to talk about, basically, is that we're using this to draw model Hamiltonians to describe some photoisomerization reactions. So far with very good qualitative results. And that's about it. If I wanted you to take home anything more than anything else, really, it's that you should look at the state, right? You do a calculation. Somebody tells you to do a calculation, your advisor or whatever. You go, you do the calculation. You really have to look at it. because it's the patterns that are in the state that will tell you, if you compare them against other molecules, what the trends really are. This is all dependent upon, ultimately, the shape of those orbitals. And then using this, you can actually find what the fragments are, right? Fragments in this particular case with the length of the bridge. And in the end, if you've done a few of these to convince yourself, you can go off and you can make model Hamiltonians and do a lot of things that you really can do with a pencil, actually. Although this might be bad for computational budgets. And with that, I'd like to thank all the people that have helped me and you paying attention. Cheers.
Many questions, but first question as a chemist. I know acidity and basicity, you have protons and Lewis acid, right? So, Brooker Basicity and bases and Lewis acid bases. That's about either donating or taking up a proton or a pair of electrons, right? A pair of electrons is Lewis acid bases. So, what is a single electron base? Are you talking about electron affinity? Or a reduction potential?
This is a very good question.
What do you mean by
This
single
is a very good
electron
question.
base?
Depends upon the dye, right? So I said that you could obtain a solution to a particular CAS-SCF problem. It looks a lot like this. It has 3 orbitals. At convergence, the orbitals are broken up as so in a localized basis. Actually, the orbitals in the active space in the CAS-SCF can be rotated without affecting the state. So you can choose the basis that's good for you. This is the one that's good for telling the story that I've told you. Now, there are 2 classes of dyes. Methane dyes. You can think of them as N-type and P-type dyes. This particular dye has a very easy to obtain 4-electron and 3-orbital active space. If I were to go and do this for, say, thiazole orange, which is an asymmetric monomethylene cyanine, I would find that this was very hard to obtain, but I could very easily obtain a 2-electron and 3-orbital active space. Now, you can actually connect this to ideas that were being discussed.
You mean the one is a donor and the other is an acceptor?
Essentially.
Yeah, I think so.
Essentially.
I mean, then in the electronic sense, right?
Yeah.
A donor or an electron.
Yeah.
So
in one case, the basicity is an electron affinity, and in the other case, it is an ionization potential.
Yeah. Well, but that's always the case, I think.
Yeah.
Okay.
Did I answer your question?
Well, I think it's semantics.
Oh, yeah.
So I think, in single electron basicity is really. Are you the only person that uses that nomenclature? I've never heard of it.
Brooker used it. Platt used it.
Okay.
Pretty sure neither one were alive.
I just try to understand. Okay.
So how, the methine dyes, you have this correlation, how general is that for, say, other classes of molecules, like another simple one would be polyacenes? I don't, Platt, obviously, that's where you came up with most of those theories. And then the other question would be, the correlation, is it singlet only, or a singlet triplet, or can you get any, the homo-lumo gap that you're calculating? Does that work for any LUMO, I guess? I mean, there's only one LUMO technically, like the thing with some triplets.
Actually, part of the point is that there may not be only one LUMO.
Okay.
But you can, if you, and part of the point, I guess, is also this, is that if you want, is that the solutions you can find are dictated by the structure of the molecule that you're looking at. And yeah, you can find triplet solutions to an active space problem that's very much like this, and the orbitals are very similar, right? This is telling you something about the molecule. It's telling you something about the structure. I haven't actually calculated the triplet energies for a dye set like this and plugged them into Platt's model and seen if they also produce the line. I think they would, just standing here and answering your question. But really, it is general in the sense that really when you get a solution like this, this is telling you something about a separation of timescales. Right? It may have been obvious looking at it to begin with. Right? I mean, the electron motions and correlations within the ring occur on a qualitatively different time scale than those between the ring and the bridge. For polyacenes are complicated. Right? I mean, you don't have all the time quite this separation of time scales, and this is related to what Jeff was saying. You have then degenerate orbitals. But I would say that you can still, if you want to make a qualitative model, of polyacenes based on one-electron states, it's pretty clear that you would need at least 4 orbitals, because you would need enough orbitals to produce the LA, the LB, and what are they? The A and the B, right? So yeah, if you do that, if you have a set of polyacenes, you find their LA and LB, AB orbitals, then, and you do this for a whole set of molecules, which is probably been done. I mean, then you've got the basis for model Hamiltonians, essentially, like Platt's model. And you can, does that answer your question?
Well, you think the answer is yes. That it could be generalized.
Yeah.
More complicated for most electrons.
Yeah. The underlying message is that if you look at the state, pay attention to the state, then you can find trends that you may not necessarily find if you are just comparing series of particles.
Yeah, when you came to Bondlength alternation, I was thinking about all the calculations by Jean-Luc Légat, especially when it comes to conjugated polymers. So, is your analysis or your way of analyzing different from what you did?
In a way, yeah. If I remember from what Breda and also Marta have done, they often choose an origin for the bond length alternation coordinate that is essentially the average of the bond lengths. One of the things that comes out of this model is that may not be the most ideal choice of origin. Because what this model actually says, no, this is not the slide I wanted. I mean, I probably could explain with this, but for a dye that is asymmetric, but near resonance, BLR will be 0. And so the bond length alternation will also be 0. But really, this bond length alternation is referenced to the lengths of the symmetric dyes. And it turns out actually that what this says, you might not notice this for a long chain polymethane, but for a monomethane, an asymmetric dye near resonance actually has a bond alternation still, because each side of the molecule converges to the bond lengths of the appropriate symmetric dye over the right domain. So what this is saying is that even at resonance, there is an alternation, because each bond is referenced. So the zero of this thing, basically, for every bond, is the bond length of the corresponding symmetric dye. Is that clear? So I mean, it is very similar. It actually is very similar, and it's
Well,
a two-state model.
It gets more complicated when you have an asymmetric dye to start with, right?
Mm-hmm.
And so if you have the real cyanines that are totally symmetrical, and you then play with Hammett equations, then you have at least a symmetric starting point, right? And so
Yes.
then everything is totally clear. You have more complicated situations, which are of course also more interesting.
I think so. Well, actually, I think that what they do is very interesting. But yeah, I think, and you wouldn't notice this for a long chain die necessarily, because once you have long enough chains that the atoms in the middle are not really feeling the asymmetry of the ends, then this is all pretty much going to fade out. Right? So then, even for the two different symmetric dyes, the dyes near the middle should be ideal resonant carbon-carbon.
Okay, we should move to the next section, and please join me to thank Seth